Hello, good people. I'm finding the front page here of 6.11, which is integration by parts. And so we are still in the section where we're learning different techniques of anti-differentiation. And this integration by parts is really what we would use whenever we're multiplying functions. And so just a quick recap over here on the side. Remember that when we were multiplying functions, I couldn't just take the derivative of the first times the derivative of the second, right? So we had to use this product rule. So when I was multiplying two functions, I would just take the derivative of the first times the second plus the derivative of the second times the first. So there was a special rule that I had to use in order to find a derivative. We could not do just the derivative of the first times the derivative of the second. So this was not correct. There was a special rule for that. Well, the same thing with integration. When I'm multiplying two functions, I cannot just take the antiderivative of the first times the antiderivative of the second. That's not possible. So what we're going to use is something called integration by parts, which is a direct result of the product rule. So just as a quick recap here. So the product rule again says if I'm multiplying f times g and I want to find the derivative of that, take the derivative of the first times the second plus the derivative of the second times the first, right? But if I subtract this part on both sides of my equal sign, well, now I'm left with f of g prime minus f prime of g equals f times g prime. But I want to take the antiderivative. So when I take the antiderivative of this side, I have to take the antiderivative of this side, right? Well, here I have two parts, so really I can take the antiderivative of that. And in so doing, here, when I take the antiderivative of something that is being differentiated, I'm going to be ending up with fg minus the integral of f prime g, and that's going to equal the integral or the antiderivative of f g prime. So this is really f of x times g of x, and then minus the antiderivative of f prime of x times g of x. Now, integration by parts is also known as UV substitution. So remember, we had U substitution, which was a way for us to make our setups, our integrands a little bit simpler. Well, UV substitution does the same thing. And it really uses this idea, which is the product rule kind of solved for one of the parts. And so when we do UV substitution, it looks something like this. And it's the same idea. We're going to take the antiderivative of u times dv, and that equals u times v minus the integral of v times du. So it's the same idea where we're taking the derivative. I'm sorry, we're taking the antiderivative, but we're going to do it in parts here. Now, this takes practice, obviously. So the more you practice, the more patterns you see. But we're gonna basically stick to two things. Number one, I'm not gonna use this formula here. I'm gonna use the purple UV formula. And so I need to, whenever I see that there's an integral where I'm multiplying two functions, I need to identify which function is easily differentiated. Which one can I take the derivative pretty easily? And as important is which function can I anti-differentiate very easily. So I'm looking for to debate which of the two functions, and mostly we're going to go first with which one can I anti-differentiate easily, because I need to find the antiderivative of one of them, and then which one can I take the derivative quickly and easily as well. Okay, so we're going to try this UV substitution. I know the notes page is pre-set up with f and f prime and g prime, but let's not use these. Let's use u and dv, and then we're going to find du, and we're going to find v. So I'm multiplying x times sine x. So I have two functions, right? And so my question is, which one of these is easy to differentiate? Well, they kind of both are. And then which one is easy to anti-differentiate? Well, they kind of both are, right? But one thing you might want to, and here, if I change my f's and g primes, I'm going to say this. Oh, let me change colors. In order to identify u, we should choose something that becomes simpler when you differentiate. And in order to find dv, we're going to find something that can easily be integrated. I also want to choose u if it's something that I can differentiate and differentiates down to zero, right? If I take enough derivatives, will it get me down to zero? And the answer is yes, if I choose x to be my u and dv to be my sine x dx, right? Then when I take the derivative of x, that's going to be 1 dx. And when I take the antiderivative, so I got to take the antiderivative of sine x dx, that's going to be negative cosine x, because the derivative of negative cosine x is positive sine x. So now that I have this, the formula says if I want to find the antiderivative of x times sine x dx, which by the way is u times dv, this is u, and this part is dv, then that equals u times v, So that would be x times negative cosine of x minus the integral of v du. So the antiderivative of v times du, which is just 1 dx. Okay, so this part is what I need to figure out. Well, this part is already taken care of. I don't have to take any antiderivatives here. I'm just multiplying x times negative cosine x, and that's negative x cosine x minus. Well, I have a negative here in my integrand, so I'm going to factor it out, and when I do, it becomes a plus. And then I'm taking the antiderivative. Now that I've plussed this out, it's going to be the antiderivative of cosine x 1 dx, or just cosine x, and that's sine x. Add a c, and we're done. So using the product rule, we can set up a formula called integration by parts. And again, some people call it UV substitution because I'm using a U and a V and a DV and a DU to figure this out. But this setup right here in purple is what you need to remember. That I'm multiplying two functions and I'm wanting to find the antiderivative. Can I find the derivative of one easily? Can I find the antiderivative of the other easily? And then I set them up as U times V plus the antiderivative, minus the antiderivative of v du. It became plus because there was a negative inside the integrand. So what I'm claiming is if you take the derivative of this, you get back to where you started. Is that true? Well, you can try it when I turn off the video. Take the derivative of this and see if you get back to x sine x. We'll look at another example and we'll practice that UV substitution, also known as integration by parts.